Let me illustrate these ideas with some simple demo. So this is our typical relief of the real u function. And this is the initial position of the contour. And as you see, this red dot is a saddle. Now what is happening? So this is how we deform the contour. And as you see, so this is the steepest descent direction, right? So, and basically, let me show you probably in a more transparent way. So this is how it is defined. So now it's fully transparent, and this is the steepest descent direction. All right. Now let's actually write down what we got. So here is our equation for the steepest descent direction. So where phi is the argument of the second derivative, and alpha is the angle which fixes our direction. So alpha is equal to pi by 2 minus phi by 2 plus pi n. Right. So you see this, there is ambiguity because n is integer. And basically, we have two directions. So what is happening? So this is the initial position of our contour. This is the saddle. And these are two possible steepest descent directions, right? Because we can go down from the saddle in this direction or in this direction, right? So it's quite natural. So which one to choose? Well, it depends on the initial direction of the contour. So, for example, you may use that kind of deformation, like that, and choose, in this case, the rightward steepest descent direction. Or you may try to imagine that you go crosses the saddle point in the opposite direction, right? For example, when n is equal to 0 and 1. So in this case, the deformation looks a little bit weird, but right now we can't exclude it. So like that. So the second possibility looks definitely a little bit weird, but still there is always this choice, and we'll decide which direction is correct in a second. So to figure out which direction is correct, let me show you another demonstration. So here we go. So this is the initial position of the contour and two possible choices of the steepest descent direction. But in reality, if we switch to the relief of our u function, let me make it slightly transparent. Right, so this is our deformation of the contour, and the red regions here are the ones which are underlined, which show you the regions of u relief which lie above the saddle point, and the blue ones are the ones which lie below the saddle points. So you see that this more weird deformation, it actually draws the contour through this red regions, so the regions where u function is above the saddle. But this is not what we need. Why? Because we are interested in such a deformation that when we go away from the saddle, this u function diminishes, not raises, right? So how do we find these regions? Well, at least we can find them locally in the vicinity of the saddle point. So what we do is we write down the expansion of our f function again. As you remember, it looks like this: 1/2 s squared modulus of f prime prime naught. And now there are two terms. The first term is a cosine term, the real part of our exponential of phi plus 2 alpha, which defines the change of the real part of f. And the second term defines the change of the imaginary part of our f function. Right, so we are interested in the regions where this addition to our real part, this one, is negative. So cosine of phi plus 2 alpha should be negative. Well, let's actually solve this simple trigonometric equation. Well, the solution is trivial. So phi plus 2 alpha should be constricted to the region from pi by 3 pi by 2 and pi by 2. So here is the solution, right? Alpha is greater than pi by 4 minus phi by 2 plus pi n, and smaller than 3 pi by 4 minus phi by 2 plus pi n. So what are these regions? So let's have a look. First of all, this is their steepest descent direction. And as you can clearly see, these two angles, this one and this one, they differ from the steepest descent by just pi by 4. Here you have pi by 2, and here basically it's pi by 2 minus pi by 4. And here it's pi by 2 plus pi by 4. So now we know what is happening. So this is the steepest descent direction, and the blue regions, the regions where the relief of our u function lies below the saddle, are these ones. So they are just have this pi by 4 angles on each side. So these are kind of allowed regions through which the contour should pass, right? The additional regions come from, so the initial region comes from n is equal to 0, so pi by 4 minus phi by 2, and 3 pi by 4 minus phi by 2, this one. And the second region comes from n is equal to 1, so it rotates by pi counterclockwise, like that. So, and now, of course, you see that that kind of passing of the contour, that kind of deformation, is illegitimate. Why? Because here the contour passes through the allowed regions, and here the allowed regions are like that. But the contour here and here clearly passes through the forbidden regions, and this is not good at all. So this is how we chose the correct steepest descent direction. And finally, we are ready to write down the answer for our estimate. So I of lambda now is equal to the integral. So we made this parameterization. Now z, as you remember, is equal to z naught plus s to e to I phi. So dz is equal to ds times e to I phi. As usual, we substitute this curved contour with a straight line with the slope phi, which is defined by the steepest descent direction. And the remaining integral is simply Gaussian, because it's e to lambda f of z naught plus this small addition, but cosine is -1, so we have just simple expression like minus 1/2 s squared lambda f prime prime naught. And as you remember, always there is an additional function g of z, which we approximate by its value at this z0 point. And here you go. We just can take this integral, and this is the final answer for our asymptotic estimate. So it's so the Gaussian integral, it's square root of 2 pi by lambda f prime prime 0. Right, and e to I phi e to lambda f of z naught g of z naught. So here it is. Here is how the asymptotic estimate for the case of complex value functions is made. So now let's discuss some examples.